Today I would like to present the mini project of electrical machine design. Our project number is 22. We would like to present about the 80 slot and 60 pole permanent magnet brushless motor. My name is Muhammad Ghairi Hakimi bin Maher, and my fellow friend is Tan Kian Han. For the introduction, this is the construction of permanent magnet brushless DC motor. It consists of two parts mainly. There is stator and rotor. The stator is made up of silicon steel stamping with sluts. The sluts are accommodated armature winding. This winding is wound with specified numbers of poles. This winding connected a DC supply through a power electronic switching circuit. The rotor accommodates the permanent magnet. The rotor shaft carries a rotor position sensor, and the sensor provides information about the position of the shaft. This shaft position signal sent to electronic communicator. So for the advantage of permanent magnet brushless DC motor, there is no mechanical commutator, so that the size becomes very small. Speed can be easily controlled. Regenerative braking is possible. For the application is the automotive application, textile and industries, computers and robotic, and also small appliances such as fans, mixer, and etc. So this is the comparison between conventional DC motor and permanent magnet brushless DC motor. So for the maintenance, the conventional DC motor is high, but for the PMB LDC motor is low. For the commutation method, the mechanical contact between brushes and commutator. For PMB LDC, electronic switching using power semiconductor devices such as transistor and MOSFET. For detecting method feature, automatically detected by brushes for the conventional DC motor. For PMB LDC motor, rotor position can be detected by using sensor. For example, Hall sensor and optical sensor. For controllable conventional DC motor, the speed is controllable is difficult. For PMB LDC motor, speed can be easily controllable so that it is possible to have very high speed. So this is the dimension of rotor that we designed using AutoCAD software. And this is the dimension of stator also using AutoCAD software. So this is the model that we simulate from Opera 2D. That is 80 slots and 60 pole model.
Hello, I'm Kian, and today I'd like to explain the simulation result based on the design for the brushless DC motor, and we simulate in the Opera 2D. And the figure shows the magnetic field distribution across the brushless motor, and it counts with the magnetic field distributed evenly across the motor, and it shows that the pulling force across it has distributed evenly, so the motor can rotate very nice. And then next is the magnetic field distribution, and the figure shows that the magnetic it shows the maximum flux density across the motor based on the simulation, and the result comes with the 1.492 Tesla, and is below the midpoint of saturation as B set of 1.65 Tesla, and we can conclude that the motor has designed optimally. Move on the vector map. The vector map shows the direction of the magnetic flux flows in the motor, and we can see that magnetic flow from North Pole to the South Pole and South Pole to the North Pole. next one is the mid-air gap flux density in VR component. What is VR component? VR component is the radial component of magnetic flux density in the mid-air gap. From the graph, we can see that the magnetic flux density across the mid-air gap was 0.8267 Tesla, and it can be verified using the calculated average mid-air gap density of 0.8296 Tesla. Then move on the magnetic flux density in BT component. The BT means that the tangential component of the magnetic flux, and it shows that the maximum flux density is 0.4 Tesla. In order to run the motor, we need to estimate the coking torque. The coking torque is generated when the side of the rotor teeth line up with the side of the stator teeth in the motor, and it produces the coking torque. This coking torque is undesirable, and it will cause the ripple output to the output torque of the motor. And then from the simulation in Opera 2D, we count with the graph. It shows the maximum coking torque during the rotation is 0.031 Newton to negative 0.031. From the graph, we can conclude that the coking torque during the rotation may not affect the output torque because it's only small effect for small value. And move on to induced phase EMF. And from here we can see that the shape of the induced EMF is sinusoidal, and the waveform can be used to predict the output torque of the PM motor. And the sinusoidal means that the output torque of the motor can be smooth and minimize the losses of this PM motor. Okay, move on to conclusion for my friend.
Okay, for the conclusion, the design of brushless DC permanent magnet motor has been simulated in Opera 2D software and shows result as follows. The magnetic field distribution across the motor distributed evenly, which result in balanced pulling force in the motor. The motor also can operate in maximum flux density that below the knee point of saturation curve. During open circuit, the simulated result of mid-air gap flux density was verified with calculated result. So the coking torque occurs during the rotation will not affect the performance of the motor. The sinusoidal waveform of induced back EMF gives a result of smooth output torque with minimal losses. Thank you.